Thank you, Hans. Thank you very much for inviting us to speak here. So we have heard a lot of redundancy and robustness in the multiplexing head end, and we will now, Tork and I will now cover how to get the output of the multiplexers to the transmitter network. So we are talking about DAB distribution. Who are we? So to WCOM is a German company located in Flensburg, and we handle broadcast contribution and distribution for various standards, including DAB. So for DAB, we do basically everything except for multiplexing and transmitters. So we take care of getting the audio from the studios to the DAB headends, and we take care of getting the multiplexer output to the transmitter network. We have hardware and software solutions, which are used by the broadcasters and network operators, service providers worldwide. The output of the headends is delivered in various formats. So historically, we have seen a lot of E1 lines. So this means coax lines. Sometimes microwave links are being used. Tork has spoken about satellite distribution for DAB in 2023 in this NICS seminar. Our focus today will be distributing EDI over IP networks. Wrong button. So IP distribution means that we take the DAB ensemble output from the multiplexer, which is the ETI format, and put those ETI frames into IP, which is done by EDI, which is a specification to encapsulate those frames into an IP stream. And it is based on the distribution and communication protocol, which is DCP. DCP is the protocol which handles the robustness in EDI. So that's more or less the transport layer, which does the fragmentation and the robustness of the EDI distribution. Looking at IP, so not IP is not the same everywhere. So what does IP actually mean? There are some large operators which have their own wide area network, their own fiber, their own MPLS. Sometimes you have rented IP connections which are carrier managed. At the other side, we have increasing requests of customers who want to use the public internet or even mobile networks for DAB distribution, be it for backup feeds, be it for very, very remote sites, and other things like that. So how do we make that EDI distribution to the transmitters robust? Within EDI and DCP, there are several methods. We have forward error correction, packet spreading, a packet resend, which is rarely used in practice, and we have the possibility, which you have seen, of dual streaming. So what is forward error correction? Basically, in simple words, it's adding additional information to the stream, so that on the receiving side you can repair the stream. And it does not require a retransmission, it just adds additional information. And it has a known data rate, which increases due to the additional information, and a known latency. In addition to forward error correction, you can use packet spreading. So we are seeing on the slide, we are seeing the packets which belong to, let's say, the EDI frame. And they would be output without spreading, they would be output in small bursts. So every 24 milliseconds, you will have a burst of fragments. This will mean that your especially if you have maybe multiple multiplexers in your network and all will do output at the same time, you will have a very bursty network. So when you introduce packet spreading, you spread your packets over a certain time frame. So if the time frame is 24 milliseconds, which is the AF interval or the ETI frame duration, then you will have a constant spread of packets. You can even increase the spreading further, which will lead to interleaving of the packets. So the packets of different blocks will interleave with each other. So how does it help us for robustness? So if you have a network error, this will lead to packet loss. And if I'm unlucky, the packet loss will, in our example here, will affect the complete block of, so all packets of a block will be lost. So with packet spreading, we will have only in our example 3 blocks which are affected. And depending on the FEC level which we chose for the correction, which I've explained further, this will require FEC level 3. So FEC level 3 means we can lose 3 packets of a block and they can be reconstructed. In our example above, we will need a higher FEC level to have the same result. With spreading, this situation is even easier because fragments of different blocks are affected. So in our example, only they belong all to 3 different blocks. So it's even easier to use forward error correction. So as a result, a recommendation is, so FEC adds additional information. It is good if you have sporadic packet loss, but at the other side, it increases the bit rate, and increasing bit rate, especially if you have congested networks or if you have a rented IP connection with a limited data rate available, it can even worsen if you have overload situations. So it doesn't always make sense to increase FEC because it can make it even worse. Packet spread helps if you have bursty losses. So before considering increasing your forward error correction, consider increasing the packet spread. I don't have to tell much about this here. So what we call dual streaming is basically sending out 2 identical streams over either over separate networks for redundancy, or you can send it with the time offset. And this is what Wolfgang and Lars Peter already have explained. It makes it even easier to take fragments from the different stream and build a continuous output stream out of it. So the built-in features in DCP and EDI help us a lot for managed IP connections. So we are fine with our own WANs, we are fine with the managed IP connections, but as I said, we have requests for using public internet and mobile networks for EDI distribution, and this led us to the development of EDI over SRT, which Tork will have a word on. Just a short word on this specific use case here. Consider you have a satellite distribution, but due to weather conditions, the satellite receivers at the transmitter stations, which receive the EDI feed and for the transmitter, they, due to the weather, they might not receive it correctly. And for that case, customers want to have a backup feed, which shall not cost a lot. You don't want to have a fiber up to the mountain. You just want to have a backup feed. And that's where SRT came in.
Thank you, Arne. Hello. I will give you an introduction to secure reliable transport, tell you something about how you can tweak your SRT connections, give you an end-to-end system overview, and at the end, some key takeaways. SRT is when transporting EDI, SRT adds another layer on top of UDP. And SRT works in a way that sender and receiver takes an active role. So SRT, when used SRT, packets are detected as lost and they are retransmitted within a configured latency window. SRT is typically used for unicast direction over the internet, and you can do something like a bridging. So you can transport your EDI stream over SRT over internet links and then feed them back as multicast feeds to your own network to bridge a certain type of backups. So that's typically used for. And SRT can have data packets and control packets. And these SRT data packets have a packet sequence number to detect lost packets and some timestamp info to maintain timing deadlines. And one important parameter of SRT is the round trip time. So SRT controlled packets measure the round trip time and they are responsible for sending a negative acknowledgement for loss recovery. I will make some side notes because SRT is very similar to RIST, another redundancy protocol. So reliable over internet stream protocol is very identical, but can also be used for multicast connections. So I always make some side notes because SRT and RIST are very identical, where RIST is an open source protocol based on RTP. As both protocols involve SRT and RIST, they also have encryption support, congestion control, which can become very handy because this retransmission can be very aggressive from time to time. And SRT and RIST are based on the same mechanism, and it's called automatic repeat request. It's called reliable layer over UDP. And here are two of the important parameters when tweaking SRT connections. So basically it's working in a way that SRT sender is sending out packets with a SRT sequence number. And the first parameter is to declare when a SRT packet is declared as lost. For example, with a max reorder tolerance of 1, directly when the first packet after a missed packet arrives, a negative acknowledgement is sent, and then this packet is retransmitted. And with a max reorder tolerance of 3, the detection delay is delayed by 3 packets after a missed packet. So that's something you can tweak how aggressive you want to have this negative acknowledgements. And all this must take place within the SRT latency, that's a receive deadline. So a constant playout buffer is built up and packets are forwarded to the application based on this scheduled delivery deadline. And when this request retransmit does not take place within this SRT latency, then this packet is not forwarded to the application to prevent some kind of stalling. Here I have example for EDI transport. And it's something I want to show about delays because SRT is typically adding a delay on your connection. So in DRB, we have a heartbeat. It's 24 milliseconds, an ETI frame is generated. And in this example with FEC level 0, 3 packets are generated 24 milliseconds wise. And the detection delay in this example, if a packet of sequence are sent and a returns of 4 is set, is 72 milliseconds. And there's a general rule, as a general example, that you have the detection delay to detect when a missed packet is missed, and then you have the recovery time. And the recovery times, as a general rule, is 2 to 4 times the round trip time. So round trip time is the most important parameter when it comes to SRT connections. And in this example, you add up by a latency of 112 milliseconds. And what is important to know is that these SRT retransmissions are not limited to a single request. Recovery attempts continue until the latency deadline is reached. So it is very handy to cap the SRT bandwidth, and that's SRT bandwidth parameter. And it's very important to cap your bandwidth if you have a limited connection capacity, because otherwise this can lead to some kind of stalling. As a side note, the SRT payload can either be the PFT layering, so you can transport your DCP fragments over SRT, over the SRT protocol, or you can directly insert the application frame without the fragmentation. And what we typically do is to have a FEC level conversion. So we do not know which EDI FEC is coming in. So we convert it to a defined FEC level with a certain amount of packets, and then insert this DCP packets over this SRT protocol. So there are two flavors how you can transport that. So there are some timing challenges. SRT is typically adding a minimum delay of 120 milliseconds to the all transmission chain, and it may be required to increase the ETI test offset for that. So typically when we have set up SRT connections with our customers, it's very often that the ETI test offset must be increased to accommodate for this SRT latency. And typically, if you have enough latency, then you have a very reliable transport network. So everything is basically matched on the round trip time. You have to measure your round trip time and to measure the max peak of your round trip time. Then you can set up a low amount of this max reorder count, and you have enough latency left. Then the setup is really reliable working. And you need enough bandwidth. Here's an example that typically we set up this SRT connections with our customers, and then we check about retransmitted packets, reconnected packets, round trip time, and so ongoing. And it's very handy to also measure the transport compensation delay, because you can measure the time the transmitter stores when you compare the ETI test against the actual NTP time. So our downstream equipment has a direct thinking of what the transmitter stores. And if there's a wraparound to the next second, you can see this transmitter compensation delay is wrapping up. So the transmitter compensation delay is sinking. The SRT latency is increasing and then wraps around and is back up over 900 milliseconds. And that's a totally failure scenario that you have to jump to the next second. As some key takeaways, SRT, or also RIST, which can be used, adds reliable automatic repeat request recovery on top of UDP. You have to measure your round trip time and to define your SRT connections due to this round trip time. This max reorder tolerance adds some kind of delays the loss detection. And you should provision enough bandwidth headroom to have a stable operation. And if you set up this SRT connections, which are really working fine, if you have enough latency, it's not a problem. So you have to make sure that the overall system is matching. So proper round-trip type measurement, sufficient headroom, and correct latency sizing are essential for a stable EDI transport over SRT. I come to the next topic, which is EDI redundancy switching. And Lars Peter and Wolfgang explained some principles of the multiplexer. So that's really great. I do not have to explain a lot because you have all seen the syncing of the EDIs and all how this magic works. So I come to a general example what we did with a Panida multiplexer, and then to a general examples with all multiplexers. So typically what we have is when you have a EDI PFT seamless switching, you have two EDI feeds from two derived multiplexers and they are synced. So this EDI feed, which is sending from these transmitters, from the multiplexers as bitwise the same. That is very important. Because one potential case with SFN networks is when different transmitters are sending different data. In that case, the SFN is broken. So this can happen if the process EDI is generated from MUX A and forwarded to a B transmitter and MUX B and forwarded to different transmitters. And these are, for whatever reasons, these multiplexers are not in sync. The sync link is, for example, broken or there's something misconfigured. And it's very important to being able to signal this information to the downstream equipment so that we're absolutely sure SFN is absolutely working fine. And what we see is we have two incoming EDI feeds, but how can we detect from which multiplexer the EDI feeds are derived? So in typical, and that's good that I do not have to explain this because in bitwise, both multiplexers when in sync handle the same feed. So bitwise, the output for multiplexer A and B is the same when in sync. And this can be signaled by either using the ETI error field, for example, error field 0 for the primary marks, but there's something better that we can do. And we add EDI transport extension, which is in the EDI standard, and that's the PFT source address. And then simply, when the EDI feed is derived from multiplexer A, the source address is set to 0. And in the case it is derived from multiplexer B, is set to 1. This is really handy because you have a really fast detection and you know what's ongoing in your EDI network. Because for whatever reason, disk failure, network linking problems, you know exactly the state of your downstream equipment. So you can see, okay, you have EDI input 1, PFT source address 0, great, it's derived from multiplexer A. And if things happened and something is broke down for whatever reason, then our downstream equipment clearly signals, okay, this EDI feed is sourced from multiplexer B. And that's really important information to know because for whatever reason, if this EDI feed is then sent out to the transmitter, you're absolutely sure that SFN might be potentially broken or not. In general, when it comes to ETI seamless switching, you can do it on both levels. So in most cases, it's the PFT sequence numbers that are aligned, and you can do all this dual streaming, but you can also do it on top of the ETI frame level. So for a general overall wrap-up, I will hand over back to Arne again.
Yeah, thank you, Tork. Yeah, I just want to wrap up our presentation. So we have seen how the built-in functionality of EDI DCP can help us to increase the robustness in managed IP networks. We have seen dual streaming again, and we have seen how SRT can add another method how to get the streams to your transmitter network. We have had a deep dive into the way how we do seamless EDI switching together with Paneda, for example, in the IKEVA network in UK. We would have loved to talk about another topic, which is backup switching at the transmitter sites with our equipment and how to remote manage that with software, which here we have developed. But we don't have time for that. Maybe this is a topic for the next seminar. Thank you very much.